Hello. So I'm going to talk about ZFS containers, and I'm going to attempt to condense exactly 20 minutes of content into 20 minutes time. So I'll do my best. So I've architected a project which can be built upon during the hackathon. These are the URLs to the GitHub project and also to a Vagrant image, which will let you use OpenVZ and ZFS simultaneously. So my goals around this were to, so my goals today, or now, are to introduce this project and image, which may be used for inspiration or further development in the hackathon, to demonstrate some practices for efficiency, an alternative to ZFS dedupe, which is known to be expensive, and to suggest some enhancements upstream, which can enable some additional use cases. And the initial motivation is that I couldn't find a great tool in doing ZFS synchronization, nor a common practice of combining ZFS backend with OpenVZ. And I wanted to incrementally address ZFS sync in my own way, because there's many different complexities to this, without implementing any kind of synchronization across hosts of your data sets. You have divergence of your data, inefficiency in its transfer, and inflexibility in expressing what changes you want to propagate. I wanted to advocate ZFS as a backend for a variety of reasons, and reduce the barrier to entry for new use cases. And dedupe is known to be expensive, so there's other ideas around that. The project's aim is to make it transparently easy to use. One command to say I've made a change to my data set, and I want to snapshot it in time, or I want to derive something from it. I'll go into more detail on the container aspect next. But I also wanted the project to be versatile and flexible, efficient in terms of incremental transfer, and a notion of dedupe that I'll explain later, to enable some kind of greater privacy through a data set injection that I describe later, and to advocate that this may be very well used in a dev build production environment. In a dev environment, you get perfect fidelity by synchronizing the exact snapshots. In production, you gain efficiency by having a common starting point, and your incremental release is a small delta from your starting point. So I leverage ZFS and OpenVZ together. And briefly, OpenVZ is similar to Docker. It's a container technology into which you may put an OS image and an application. OpenVZ adds the ability to checkpoint your state, which is handy for debugging or for failover or migration, things like that. But under the hood, the same principles can be applied with Docker and CRIU. I leverage ZFS snapshot, clone, send, and receive, these basic functionalities. Basically, it's copy on write that I leverage. With ZFS, you get the ability to inject, consider orthogonal data sets. Your home directory is orthogonal to the container. Speed-wise, ZFS is very efficient. Turns out to checkpoint your entire OS image in OpenVZ is very efficient. If you're only using 200 megabytes in your applications, it'll write a 200 megabyte image representing your whole OS state. And in contrast, sending a full VM of your entire OS may take 8 gigabytes or 16 gigabytes or whatever it is, making it problematic to do direct checkpointing or migration. And the whole use of snapshot and clone is very fast and efficient in ZFS. So I observe a practice, which is an example of a use case. It can be generalized, but this is an example for this discussion. So I have a core starting point, a data set, which is like a container image. It's like a entire OS Debian 7 starting point. Within OpenVZ, it appears within a hierarchy with the ZFS as a backend. That core starting point 1007, I call it, is cloned, copy and write, and becomes the basis for a intermediate common packages like container data set. meaning like if most of my packages include the build environment, this is an efficient intermediate point for encoding. And then from that, I have specific containers. Maybe it might be a web server, a build environment, and these are lightweight to encode relative to the 2007. And this is just what it looks like under the hood. I constructed a root directory, meaning within 1007, here are your sbin, etc. Your dump is a single file. And to clarify some of the assumptions around this, I assume that derivative hierarchies are largely additive. If we have a starting point of your base and then we have a build environment, largely we're adding content. It's not true all the time, but it is true by construction or in this particular use case. And because there's a commonality, the way that Debian or other software pulls in dependencies, there's identical content that's actually shared between these containers that would otherwise be isolated. And I choose this intermediate point deliberately to be efficient. And last assumption is that size of data is larger than size of metadata. This is just showing, more concretely the structure of the actual content of the data set. So just to be clear, like this is one example. Up to the root point of root, this is one ZFS data set, and then up to the dump is another ZFS data set. And likewise, when I checkpoint, I may checkpoint on a daily basis or when there's an update. This is just showing it's a recursive snapshot, and then there's a serial notion of like checkpointing over time for a fixed container. This indicates how I basically start with a basis, derive an intermediate point. I take the example of build essential, which like pulls on a lot of packages. And then from this 2007 intermediate point, I add a small addition, nginx. And this is done through clones and snapshots. Here's another example, Apache. Different container ID. 2007 is the common starting point. And one obvious claim is the footprint, the storage footprint with using this ZFS ecosystem is that your size of storing this is more efficient, also more efficient to send and to know what actually is differing in your intermediate containers. So when I say 5007 given 2007, it's considered a incremental delta from 2007 as a starting point. If we were to compare this to a full concatenation of each of these, that would be duplicating a lot of content that ZFS could encode more efficiently. So this ZFS and containers, combining the two, we can do lightweight snapshot, clone, and rollback. And because we are leveraging OpenVZ, it can also include the state of your running system. So just to roll back, if we have when we take a snapshot and it includes state, we do a recursive snapshot of the 1007 data set, and it includes a dump file that is the result of a VZ suspend. So we capture the state of your file system and also a single file image representing what was running at that time. And this shows what it would look like, under the hood or like low level. This is roughly what would be done to represent that. And here's some example uses of the tool. You see, it's very usage driven. A checkpoint will, automatically snapshot and your state, and you can choose to snapshot every container that's running, every data set you've got. Choose a particular container to derive a clone from. Suppose you have got your 1007, you want to drive 2007, your intermediate container. And so this functionality can be built over time, but these are some like example commands. You can also see what's differing locally versus your last snapshot and suspend and resume. This gives fidelity of the container, as mentioned, with best practices, efficient storage, integration with the checkpoint resume of your OS and application state. And it's possible to do something that you usually don't do, which is like have an environment and then roll back. So sometimes I accumulate data, temporary data, and my file system grows and grows, but I realize it was just a temporary experiment. So this makes it easy in one command to essentially roll back. Now, the core technology of the tool is synchronization of these data sets across hosts. And to do so manually is complicated, especially involving 3 hosts or coordinating efforts. So if without that, it's either it must be done manually, or maybe there's another tool out there, but the data sets become out of sync. And that's not what I want when I have multiple hosts, and I want to essentially propagate or share a container across them. So the project identifies a common snapshot starting point. It makes your ZFS send minimal in a certain sense, and the notion of synchronization is done through primitives, a push and pull operation. With that, you can incorporate a sync. You can also encapsulate the notion of asynchronized synchronization. Suppose you want to coordinate between n hosts. If you have a peer or the central repository, you can just simply include in your practice, like synchronizing to the central place first. But any number of enhancements can be built upon this, but the core notion is a push and pull. As an example, suppose I'm working on a development environment, I notice a bug. I can quickly send the state of my running system and everything in it, dependent libraries, dependent data sets, to a developer so they can know exactly what they're looking at and reproduce with perfect fidelity. Likewise, with a production environment, a centralized repository can roll out the incremental builds, and assuming most of the data doesn't change, this can be like a 10x speed up. And again, you can quickly fork your data and roll back. A work in progress of the script is injection of a data set like your home directory. You may not like if you have a home directory, it might be part of your build environment. You don't necessarily want that evolving in part of your shared ecosystem. So in the spawning of the container, you can inject home user or whatever it may be into the container as it runs. And this tool can treat that data set independently and can choose to share the home directory. Maybe if it's temporary directory, it might exclude it entirely from synchronization. But the injection lets you consider holes or pieces within your environment that you want to consider private or do not care. So I think we have time. So there's an idea of a rebase this is the generalized idea around greater efficiency. So suppose we have a collection of containers and they live in this ecosystem. What we can do if we've accumulated that over time, maybe less efficiently, is we can rebase. We can reconstruct the identical content, but in such a way that it is efficiently encoded by ZFS through deliberate copy on write constructions. So a very simple way of doing this, so this is just the overview. So a way of doing this is you name the containers that you want as your starting point. Suppose containers 1, 2, 5, and 6 are you want to be included in your rebase. You essentially dump them all into one consolidated container. Now there will be overlap, or which won't be redundant. It will be just simply encoded once in your result, and there will be non-overlap. There will be files that differ, and there will be conflict. But the notion is that the percentage of data that may differ, for example, it's maybe your package database may differ for each individual container. For the storage footprint, that portion of the data is much smaller than what is common. So the idea is you derive a consolidated container. You clone that to form primed versions of container 1, 2, 5, and 7. And then you do a perfect fidelity rsync from the original content to the primed version. You get identical content. A deletion is lightweight in terms of footprint. And you're conserving space because you're getting a maximal notion of union. And as I said before, the part of the content that differed exists. It will be encoded with high fidelity, but it is small, so it is more efficient to do it this way. Likewise, snapshots can be rebased as well, using the same idea. There's a way to do deduplication that is not quite deduplication, but it's a version of conserving data. If we note that a file has moved, in theory we could encode that by move operation. This is just a work in progress or idea. If we do a whole file deduplication, we could figure out which files are identical across the entire ecosystem and hard link everything in the destination, and this could be even cheaper, not practical for every case, but it is an example of reducing footprint. So then there's just the final slide here is around how maybe ZFS might be modified to enhance a piece of functionality. So supposing a portion of our image, like an Nginx server, is we want it to be public, and we derive it from a common public place, and then we have our own revisions to that we want to encode with a key. So right now it's not possible to turn on encryption later, but if this were enabled, then one could encrypt with a workplace key those private proprietary changes to a public data set. Same with taking that further to the personal component. It's not perfect from an encryption standpoint because you have some known or anticipated data, chosen known plaintext. But it may achieve a useful effect to be able to add encryption. Likewise, if Debian upstream, or if we knew exactly which directories potentially contain personal identifying information, we can know exactly what to inject. We can consider temp directories as orthogonal, and likewise. And there's a variety of enhancements to the tool. I'll be adding, issues, in terms of potential enhancements on the actual content over today, later today. But also perhaps if this were taken up as a hackathon project, other enhancements can be taken up. So in summary, it's one way of doing combining ZFS containers, and it illustrates some other ways of thinking about ZFS and storage footprint. So I'm happy to entertain any questions. Yeah, so the question is how can this practically be used? How do we enable it or use it? So the vagrant image is a starting point which has a OpenVZ ZFS entire Linux distribution as a starting point, and into which you can clone the project, and that's so that's the starting point. You essentially can either do this yourself or use this as a starting point. OpenVZ is a technology you can build your ZFS into that, have that as your root, and enhance it. Does that answer your question there? Yeah. Yeah.
For the rebase operation, why are you doing this mash everything together as opposed to update 1,000 to 1,000 prime and then 2,000, in order following the graph tree?
Yeah, so there's two parts to it. So the mashing everything together will, if there's an identical file in multiple containers, it'll only be stored once. After cloning that, the clone operation takes no storage footprint. There's an incremental, like for each individual container, we do an rsync. So there's an rsync of 1,000 of container 1, container 2, container 5. Is that how you'd imagined it, or maybe I didn't understand?
Yeah, I think I see what you're doing, but
Yeah.
I mean, why not take 1,000, apply updates or, whatever, and then make 1,000 prime, then refork off 2,000, just like you did at the beginning?
Well, so because the notion is additive growth of either snapshots or derived containers, it's more efficient to go backwards in time. So if we were to go forwards in time, we'd be re-encoding things in more than one way. So as an example, imagine imagine container 5, container 6 share a lot of content that would represent the same file. If we encode it forward in that way, we're essentially replaying the same content again. If we identify what actually is duplicate, what actually is identical in the result by kind of like tarring it, then we only store it once, and then we're rolling backward. So there's many ways of enhancing this rebase, but this is just one example. Anything else?